yes, it's showing up and it's little animation, so it's all moving. So yeah, I'll give a 3-minute warning before the end, and off you go, Victor.
Thank you, Moira. So I guess at this stage, I'd normally thank the organizers, but that would seem oddly self-serving. So instead, I'll just jump straight into the presentation. And what I want to talk about today is what are the factors that affect the overall magnetic activity level of low mass stars, and specifically what is the role of metallicity. And so I'll be using the photometric variability amplitude as my activity proxy, and we've already heard a lot about this today. So all of these talks set up line one quite nicely, but I'll be looking at this from more of a global structural dynamo perspective than some of the previous talks did. Okay, so this was all work done here in University of Exeter in collaboration with Julia Roquette and Louis Amar, who are both postdocs as well, in the ERC research project Awesome Stars, which is PI'd by Sean Matt. Okay, so our current state of knowledge, or our current wisdom, is that various forms of magnetic activity, such as X-ray emission that I'm showing you here, or such as the strengths of magnetic fields themselves, can be parameterized by the Rossby number. And so what you can see here is that for small Rossby numbers, these forms of magnetic activity generally plateau or saturate out to a constant level. And then at higher Rossby numbers, these forms of activity tend to have an inverse power law relationship with them, with the Rossby number. And what the Rossby number is the rotation period of the star over the convective turnover time. And so this is just it's the characteristic time scale over which convective motions occur in the outer convection zones of low mass stars. And so it's thought that this dimensionless number, the Rossby number, encapsulates or captures the interplay between rotation and convection that's thought to drive dynamo action in low mass stars. And the rotation period is just the rotation period, and the convective turnover time is generally in the literature given as a function of either stellar mass or stellar effective temperature, with higher mass stars having shorter turnover times. Okay, so in general, activity we think is parameterized by rotation and mass through its effect on the convective turnover time. But one thing that hasn't been well studied in the literature, systematically anyway, is the effect of metallicity. And so theoretically, we can kind of ask, what might we expect? Well, if you have two stars that have the same mass, same rotation, but different metallicities, you would expect that the more metal-rich star to be more opaque, which would affect the energy transport going on inside that star, leading to a deeper convection zone and leading to a longer turnover time. And so you can see here on the left, I've just plotted 3 turnover times for 3 stars as a function of metallicity. And these are taken from this paper at the bottom here using Louis Amar's stellar structure models. And you can see that the structure models do show that more metal-rich stars have longer convective turnover times. And so if you have a longer convective turnover time, these stars should have smaller Rossby numbers and therefore should be more active. And so this is kind of the chain of logic that I want to test, that I'll be testing in this work that I'll be talking about today. And if you skip out, all the intervening steps, the central hypothesis is that more metal-rich stars should be more magnetically active. So I'll be doing this with a sample of stars from the McQuillan 2014 paper, which Timo Reihold introduced earlier, but I'll go over it quickly again. So in this work, the authors took all of the Kepler light curves for the Kepler field stars and tried to measure the rotation periods of these stars using an autocorrelation method. So they first made a 6,500 Kelvin cut, and for all the stars that they could measure a rotation period, which was about a quarter of them, they put into the periodic sample, or well, we'll call it the periodic sample, and then for the remaining 3/4 of the stars, we'll call them the non-periodic sample. So in the periodic sample, all of the stars have rotation period by definition, but these authors also measured their photometric variability over rotation period timescales. And so this is going to be our activity proxy, with the idea being that more magnetic the active stars should have larger variability because they'll have either more or larger kind of magnetic features, such as spots, to induce larger variability in their light curves. Next, we took both the periodic and non-periodic samples and cross-matched them with the Lamos survey to get metallicities for all of these stars. And then finally, we took various spectroscopic and photometric information to calculate the masses and turnover times for all of these stars using the stellar structure models of Louis Aumar. And in particular, when we did this calculation, we accounted for the metallicity when making those estimates. And then finally, you can combine the rotation period and the turnover time for the Rossby for the periodic sample to calculate Rossby numbers. So these are kind of all the parameters of interest for the study that I'm going to be talking to you about today. And the reason turnover time is in brackets is because we don't actually ever use the turnover times for the non-periodic sample, but they are calculated. Okay, so if we take the periodic sample and we plot the variability amplitude as a function of Rossby number, we can see that, broadly speaking, there's an inverse power law here, relationship between the two quantities. And so that seems to match more or less with what I showed you earlier in this talk for other activity proxies. There's a few things to point out here. First is that for this sample, our stars don't really go down to sufficiently low Rossby numbers to see that plateau or that saturated regime. The second thing is that there's this kind of dip here that we don't see in other activity proxies here at about a Rossby number of 0.3. And it's not clear the cause of that dip, but Timo Reinhold, I think it was in a 2019 paper, suggested that that dip could be because bright faculae is cancelling out dark spots, leading to an overall reduction in the variability amplitude at around that Rossby number. And then the last thing I'll mention is that if you look at this figure very carefully, you can see that there's a slight metallicity gradient even at constant Rossby number. So the points at the top of this trend are slightly more metal rich than the ones at the bottom of the trend. It's only very slight, but if you know the Rossby number was perfect at capturing magnetic activity, is the perfect parameter to parameterize magnetic activity, you should expect no metallicity dependence left over because we've accounted for that in our calculation for the turnover time. And so what this could be indicating that, it's not just the dynamo that's important. There could be other effects that we have to account for, such as atmospheric effects that we've already heard a little bit about today. But for the rest of the talk, I'll be mainly interpreting this, our results in terms of kind of the global dynamo. Okay, so I've already mentioned that mass and rotation are very important for determining the overall magnetic activity level of a star. So if we want to study the effect of metallicity, we want to kind of isolate out those other parameters. So this is our sample in period mass phase. And what I'm going to do is I'm going to bin all of the stars. So that every, for a given bin, all of the stars are going to be approximately constant mass and approximately constant rotation period. You'll also see that there are some bins outlined in red, and these are all the bins with at least 10 stars in them, which we'll come back to later. But for now, let's look at just one bin in particular, and there's nothing special about this bin. I've just picked it because it has quite a few stars in it. But because all the stars are approximately constant mass and period, then any trends we see in the variability amplitude, we should be able to attribute to just the metallicity variations across the bin. And so if we plot variability amplitude as a function of metallicity for this bin, that is exactly what we see. We have this nice positive correlation between these two things, exactly as we would expect, given the kind of theoretical outline that I went through earlier in the talk. If we look at this, the stars in this bin in variability Rossby number space, and I've also included the full sample in white on this plot, we can see that there's quite a spread in Rossby numbers and a corresponding spread in variability amplitude for the stars in this bin. And you know, this spread in Rossby number really is mainly driven by the changes in metallicity, because all of these stars are roughly the same mass and period. And so on the previous slide, I showed that the high variability stars are the metal rich ones, and on this slide you can see that the high variability stars are the small, low Rossby number ones. And again, this seems to match with the theoretical expectation that I outlined earlier in this talk. Okay, so that's just one particular bin, but what I want to do is kind of look at all of the bins. So I'm going to come back to this slide very quickly. The next slide is a bit overwhelming, so I'm going to explain it a bit before I come to it. But what I'm going to do is I'm going to take this slide, this plot, so in rotation mass space, and for every star that has at least 10 stars in it, so all the bins outlined in red, I'm going to plot variability as a function of metallicity in those bins, but where those bins lie in rotation period mass space. Okay, so that's what this looks like. So all of these subpanels within the figure correspond to one of the red bins from the previous slide, but within the bin it's showing variability as a function of metallicity, and all of the subpanels have the same axis limits as this inset on the bottom left here. Now, this inset just basically shows all of the subpanels stacked on top of each other. It's not that interesting in and of itself. And I've also color-coded everything according to its Rossby number. So what you can see is that, broadly speaking, we do get this positive trend, this positive correlation between variability and metallicity for most of the bins. There are, however, two regions where this isn't really the case and the trends sort of break down. And that's this region here, which is the low metallicity region, sorry, the low Rossby number region, and this region here, which is the high Rossby number region. Okay, and to kind of understand why that's happening, we can come back to the variability Rossby number plot. So the first region is this region here, the low Rossby number region, and so this is, you remember where we have this kind of dip, and then the second region, the high Rossby number region, is here, where we have a lot of scatter. You can kind of see that the points in this region are more diffuse, more scattered. And so because the points in these two regions kind of deviate away from this nice tight inverse power law relationship that we have here in this variability Rossby number space, that means that in variability metallicity space, the trends also sort of break down. And yeah, the trends also sort of break down. And so that's kind of the top level conclusion of my work, though, is that activity does seem to correlate with metallicity at fixed mass, at fixed rotation, with some exceptions, at least for this particular proxy of magnetic activity. So what are some implications for this? Well, we can look at how easy it is to recover rotation periods. And again, Timo Reinhold kind of covered this a little bit earlier, talking about detection fractions. So in this plot, what I've done is I've taken the periodic and non-periodic samples, combined them together, binned them in metallicity mass space, and then calculated the fraction of stars for which a rotation period could be recovered by McQuillan, 2014, in that bin. So there's two main trends here. The first is that at a constant metallicity, so in this direction, you can see that it's much easier to recover oh, before that, actually, I should say that in general, when you're trying to recover rotation periods from a light curve, it's much easier to be able to get the rotation period out if you have a larger variability amplitude. You can imagine if you have very small variability, like a very flat light curve, then you're not going to be able to pull any signals out. Okay, so just bear that in mind. Right, so at constant metallicity, what we can see is that it's much easier to recover a rotation period at small mass, at low mass. And that's because low mass stars are generally more active than higher mass stars. So if they're more active, they should have a larger variability amplitude, and it should be easier to recover their rotation periods. And that's something we've kind of known about this mass dependence before. The kind of new novel result is that at fixed mass, generally speaking, it's easier to recover the rotation period in more metal-rich stars. Okay, and so it's a similar line of logic. I've shown here today that more metal-rich stars should be more magnetically active, and so a larger variability, and again, easier to recover their rotation periods. Now, this next slide I wasn't originally going to discuss, but on the back of Timo's talk, I thought I'd just shove it in there. And so this is variability as a function of metallicity, but for a solar mass bin. So all these stars are approximately solar mass and approximately 27-day rotation periods. Again, we can see this nice positive correlation between the two things, between the two quantities. And as Timo said, the sun here is seemingly at the bottom of its very low activity, the lowest activity star in its bin. But what we can, or maybe could say, is that if we could observe the variability amplitudes for more metal poor stars, that this trend might actually keep continuing. Oh dear. Well,
Victor.
Yeah, I don't actually have that many slides left, but it has decided to crash. So bear with me.
Well, the picture's nice in the meantime.
Oh, it's going to do this. Hang on. Play from here. Okay, we're back. Right, so if we could observe stars with more metal poor stars, this trend could continue, and actually the sun might be, have a more typical variability amplitude or more typical activity compared to the stars in the rest of its bin. So that's basically all the science that I wanted to talk about. Now, if you've seen me give a talk in the last couple of years, you'll know that I like to take a hard pivot at the end of my talks these days and talk about something completely different, which is mental health. And the reason for that is because it's just going to be one slide, so bear with me. But the reason for that is poor mental health is rampant in academia. There have been various studies, like this one, for instance, that show 40% of graduate students suffer from some level of anxiety or depression, and that's compared with like a number of 6% in the general population. So this is much too high. I wager that number is actually even higher now, given that we've been in a global pandemic for the last year. And it's not just anxiety and depression, although those are the most common. It can be low self-esteem, imposter syndrome is very common, all that sort of thing. And there's often this stigma attached to having mental health conditions that can prevent people seeking help, that it makes it all the more harder to recover when you do eventually end up seeking help. And I say that from firsthand experience. So if this is something that you're dealing with or suffering from, I would encourage you to seek professional help as soon as you can, and also the support of mentors and trusted loved ones, families, friends, etc. And so this is just me kind of doing my little bit to push back against that stigma. And if this is something you're struggling from, you are not alone. It is probably more common than you expect. And that's kind of all I wanted to say on that. So just to summarize, right, so the top level result is that more metal-rich stars are more magnetically active. This has implications for detecting rotation periods from light curves, which I discussed. But this also has implications for long-term rotation evolution. And so Louis Aymar, Julia Riquet, and Sean Matt was working on this in these two papers that were published last year. So if that sounds interesting to you, I encourage you to check out those two papers. Now, something that I'd be really interested in seeing is kind of similar studies to the things that I've shown you today, but with more direct activity proxies, because the variability amplitude is a bit of an indirect one that gives you kind of some slightly strange artifacts, and it's a little hard to interpret at times. And so all of the work that I discussed today was recently accepted for publication. It's still in press, but you can find the preprint at this archive link here. So yeah, with that, I will end, and I'm happy to take any questions.
So thank you, Victor, and thank you for bringing up the mental health thing. I think that's really important too. Do we have any questions for Victor? Julian.
Yes, thank you. I was wondering, in the previous talk, Veronica told us, if I'm not mistaken, that for the small scale dynamo, we see stronger convection and stronger magnetic flux for low metallicity. And here it seems to be the opposite in a way, maybe for a more, let's say, large-scale magnetism, because this is what we see on the integrated star. Did I mix things up, or is it just that we really see two opposite behaviors? And what would be your impression on that, your reflection?
So I'm going to hold up my hands here and admit that I often find it very hard to focus on the talk before my talk. What I will say is that yeah, the stuff, the work that I've presented here is with kind of focusing more on the large scale structure, the global convection zone. Whereas the previous talk seemed to be more focused on Veronica's talk seemed to be more focused on the small scale kind of near surface dynamo. I don't actually know how, I'm not a stellar structure person, and I think I saw Veronica's hand go up, so she might actually be able to tell you more about that.
Veronica, you can chip in if you would like to.
Yeah, actually, I wanted to say that I think there are two different effects going on with metallicities. So if we increase the metallicities, our convection zone become deeper. So it might be that because of that, the global overall dynamo might be affected in a way that it operates better or is stronger, but I don't know much about it. So my studies show, however, that on the small scale, on the top of the convection zone, the larger metallicity leads to a less efficient convection, which has an impact on the smaller scale magnetic fields at the surface, which have an effect on the contrasts, but then the overall global effect might have an effect on the dynamo, but I am not an expert on dynamo action.
Yeah, so I just to follow on from what Veronica was saying, I think you've made a very good point there, which is that our work is focused more on the kind of global dynamo, but there are other effects, and I kind of alluded to it in this slide when I mentioned this slight metallicity gradient that you can see in this figure. That definitely should be and have to be taken into account to kind of get a proper holistic view of how metallicity affects magnetic activity.
Thank you. And I was wondering, maybe, sorry, while I'm at it, if you try to plot this without taking into account the metallicity in your Rossby number? Just out of curiosity.
Not 100% sure. I guess it should look worse.
Yeah, if one would do it naively, basically.
It depends on what you do, and I think Louis might be able to. I'm just directing all my questions to other people, but so if you do it naively, I think often, if you use your if you're calculating a Rossby number or a convective turnover time, usually you'll do it as a function of effective temperature, and by doing it as a function of effective temperature, you can get kind of account slightly for the impact of metallicity, because at a constant mass, if you change your metallicity, you also change your effective temperature. So that's sort of built into that a little bit. I don't think it gets you the full way there, though.
So just to comment on what Victor just said, it is like temperature, the effective temperature actually almost accounts for all the effect of the metallicity, but then a little bit, maybe like 10% difference may remain from the metallicity effect itself on the size of the convective zone.
Okay.
Okay, we have another question from Thomas.
Thanks, Victor, for a very nice talk. I was wondering if you could comment on how much, I mean, when you measure the variability amplitude, you measure the non-axisymmetric part of the activity. Could you comment on how much do you think that the axisymmetric part of the activity would play in this?
So are you talking about inclination effects? Is that what you're... Are you talking about inclination effects here? Is that what you're alluding to? Is that...
No, I mean that when you measure the variability amplitude, you measure the non-axisymmetric distribution of star spots. If you have an axisymmetric distribution of star spot, then you won't see any variability amplitude. So how much?
I don't think that's true, is it? If you had a distribution of star spots that was, oh, I see what you're saying. I still don't know. I still don't think that's true. And even if you had an axis, well, if you were, I guess, if by an axisymmetric distribution of star spots you mean kind of like, you know, a ring of star spots perfectly distributed at a constant latitude,
or a polar cap.
Okay, I see. Yeah, it's so disclaimer, I don't do the measuring of the variability amplitudes myself, so there are probably more relevant experts here to discuss that. But I think it's my understanding that it's rare to get perfectly axisymmetric distributions of spots, right? Apart from, let's say a polar cap, as you mentioned. I feel like I'm not answering this very well, but I'd be happy to talk about it more with you afterwards if you want.
Yeah. Okay.
May I add here? Or?
Yeah, go for it.
Okay.
Emily.
So to Thomas' question, I think you can never have in practice a fully perfectly axisymmetric activity which is higher than the level, say the level of the sun. So you would always have small scale non-axisymmetries anyway. If you level up the activity level of the star, then you would end up in anyway, as Victor says, a higher variability amplitude. Only if you have, as Thomas you said, maybe a polar cap which is perfectly axisymmetric and with a diffuse field but dark, then yes, I mean its effect would be not in the variability amplitude, but it will be another effect, yes. But then metallicity effects in that case would be along the lines that Veronica says, I guess, right? I mean, the small scale effects. But otherwise, yeah, I mean, it would be, still you would get a higher variability amplitude for sure. I don't know if I clarified or confused more, but yes.
Okay, thank you. Yeah.
Do you have any final comments, Victor, on that?
Can I add a little bit on what Emre said? So I guess there are basically two different effects. So it's not only probably just small scale, yeah. So metallicity might have an effect on contrast of magnetic features, right? Not only might, but we know that that effect contrast of magnetic features. That was what Veronica very nicely explained. And my understanding of what Victor was explaining, that basically not only contrasts of the magnetic features, but basically, let's say, the number of these magnetic features of the distribution might be also affected by metallicity. So both effects probably take place. Which of them is more important? That's probably something for us to investigate. Yeah, that's at least my understanding.
That's a very succinct description of my final comments, so I shall defer to Sasha.
Okay, I think thank you